Hello everyone, I'd like to introduce our work InterHand2.6M. The goal of interacting hand pose estimation is a localization of interacting human hand joints in 3D space. Most of previous 3D hand pose datasets have only considered single hand case. Some of them consider interacting hand case, but they have synthetic RGB images or small-scale images or jittering ground truth 3D poses. In contrast, our InterHand 2.6M dataset contains large-scale, real-captured, and markerless images and accurate ground truth 3D poses. To capture data, we constructed Multi-View Studio with synchronized 80 cameras in 4K resolution with 90 frames per sec. We captured 26 objects, and for each sequence, left and right hand of a single person is captured. There are two types of hand sequences. The first one is peak pose, which is a transition from neutral pose to predefined hand poses and transition back to neutral pose. The second one is range of motion, which include conversational gesture with minimal instructions. For the annotation, we use semi-automatic approach, which consists of manual human annotation and automatic machine annotation. For the human annotation, we simultaneously show 5 to 6 views to the annotator for the multi-view consistency. When the annotation is done on more than 2 views, it automatically triangulates them to 3D space and project to other views. For the machine annotation, we train a strong 2D key point detector on human annotated set and test it on all remaining images, and 3D coordinates are obtained from triangulation with RANSEC. Our machine annotator achieved 2.78 mm error on held-out human annotated evaluation set, which is significantly low. Our baseline model internet predict handedness, 2.5D hand pose, and right hand relative left hand depths. The handedness tells us which hand is included in the input image. 2.5D hand pose is a combination of 2D pose and root relative depth of left and right hand. Right hand relative left hand depth is a relative depth between right and left hand joint. To train internet, we calculate binary cross entropy loss for the handedness, and L2 loss for 2.5D hand pose, and L1 loss for relative depths. In the testing stage, we perform argmax on 2.5D hand pose and obtain right-hand root joint depths from RootNet, and then obtain left-hand root joint depths from the relative depth value. We all use these three information to obtain 3D interacting hand pose. We observe that incorporating interacting hand data significantly reduces the interacting hand errors. Adding automatically obtained machine annotated data to manually obtained human annotated data decreases the error. This is because machine annotated data cover more diverse hand pose space. Our internet outperformed previous state-of-the-art method on STB and RHP datasets without utilizing scale and handedness during inference stage. This table shows handedness average precision. As the table shows, APs are close to 100, which tells us that handedness prediction is pretty easy. The bottom table shows right-hand relative left-hand position error. The error is a little bit large. 3D interacting hand pose error is large compared with state-of-the-art DataSet-based 3D hand pose errors. Our dataset can be used for 3D interacting hand pose estimation on general images. This shows qualitative results of our internet on InterHand 2.6M dataset. And the bottom row shows failure cases. Most of the failure cases comes from severe occlusion and self-similarity. This is a summary of InterHand 2.6M. We propose first large-scale real-captured markerless 3D interacting hand pose dataset. We use semi-automatic annotation, which is effective and efficient. Finally, we observe that interacting hand data is essential for 3D interacting hand pose estimation. Thank all people for helping this work.